Hi, this is section 11.3, Use Normal Distributions. Our big question here is what are the values in a normal distribution that rarely occur displayed on a normal curve? So you're probably asking what's a normal distribution and what's a normal curve. So let's look at your frame. Okay, this is about, so using Use Normal Distributions is about, right here, using standard deviation and the normal curve to find probability. So we're still working with probability, but we're now going to use this normal curve to help us find it. Okay, so a normal distribution is modeled by a bell curve. Okay, so we're going to have this bell curve that looks something like this, and you don't have to draw this because if you look a little bit below this, this is on your notes. Okay, so we've got a bell curve that looks somewhat like this. It's called a normal curve that's symmetric about the mean. Okay, so right in the middle of this curve, we're going to have our mean. Remember, we write that x bar. That stands for the mean. A normal distribution with the mean of x bar and standard deviation of sigma has the following properties. First of all, the area under a normal curve can be considered as a percentage of the data values in the distribution or as a probability. So we can do the percent or a probability. The total area under the normal curve is 1 or 100%. So the number 1 relates to 1 as a decimal is the same as 100%. About 68% lies within 1 standard deviation of the mean. Excuse me, so if I put a couple of bars here, okay, and this is our mean minus a standard deviation, and this will be our mean plus a standard deviation. In here, 68% of our data values lie. So the next one, about 95% lies within 2 standard deviations of the mean. So if I put a couple more in here, this would be my mean minus 2 standard deviations. This would be my mean plus 2 standard deviations. And in this range, right in here, 95% of our data lies. I'll get another color here. And so about 99.7% lies within 3 standard deviations of the mean. So I'm going to add a bar here. That would be my mean minus 3 standard deviations. If I add another one here, that would be my mean plus 3 standard deviations. And within this, all of this area in here, we have 99.7% of our data lies in that range. So if something is normally distributed, our data falls into a bell curve like this, with our mean being in the very middle. So example 1, use a normal distribution. A normal distribution has a mean of x and a standard deviation of s for a randomly selected x value from the distribution. We want to find the probability. Okay, so P is our probability. And just highlight what we're looking for right here. Here's the question. We want to find the probability that our value is greater than the mean and less than the mean plus 3 standard deviations. So this is what I just drew, and we're not going to really use that because my mean is right here, 3 standard deviations above the mean is right here. So this is what we're looking for, but we can't really tell the percentages on this one. So I'm going to look at this next graph. Here's my mean. Here's 3 standard deviations above the mean. So we're really looking for what percent of the data lies in here. And if you look, we've got 34%, 13.5%, and 2.35%. Okay, so I'm going to do 34%, 0.34, plus 13.5%, 0.135, plus 2.35%, that's 0.0235. And if you add those all up, you get 0.4985, or that's 49.85%. So we're really trying to find, we're going to be doing probability, and we're often looking for a range of values. So let's look at this next one. It says a normal distribution has a mean of x bar and a standard deviation of theta. Find the indicated probability for a randomly selected x value from the distribution. So our first problem here, we want the probability that our value is greater than the mean. Okay, so here's our value. We want it to be greater than the mean. So that's really, our mean is right here in the middle, okay? And it's going to be bigger than all of this stuff over here. Okay, so if we look at that, this little piece right here is 0.15 of a percent. Okay, the second piece, the next piece is 2.35%. This next piece is 13.5%. And this larger piece is 34%. Okay, and these are just values. I'm finding those because they're the normal values. They're always the same for a normal curve. So I'm going to add those together. So I'm going to do 15% plus 2.35% plus, and notice this time I'm adding them as percentages, and then I could change it back to a decimal. Didn't do it either way. So this time I'm just adding them as percentages, and if you add those up, it equals 50%, which is what it should be, because half of your values should lie below the mean. So it's 50%, or you could write it as a decimal and put 0.5, 0.5 I should say. So either one of those would be acceptable answers, but that's what you would expect, because half your values should fall below the mean in a standard normal distribution. So looking at the next one, we want the probability that our data is greater than the mean, but less than the mean plus 2 standard deviations. Okay, so I'm going to change my color, use a different color here. My mean is right here in the middle. Here's my mean plus a standard deviation, and here's my mean plus 2 standard deviations. Okay, so I'm looking for everything from here to here. So in here lies 34% of the data, and in here lies 13.5% of the data. Okay, and I'm finding those values. If you're a little bit confused, where is she coming up with those numbers? Okay, here's our curve. Here's our curve, and if you just look at the table right above, look at the box right above here, for our standard normal curve, there's percentages written for each of these pieces, and they're written right above here. So for this example, I'm going to do 34% plus 13.5%, and that's 47.5%, or if you write it as a decimal, it'd be like this. So either one of those answers is acceptable. For our next one, we want the probability that our value right here in the middle is greater than the mean minus a standard deviation, but less than the mean. So here's my mean, and here is my mean minus a standard deviation. So we're really just looking from here to here. We're looking at this value. So if you look right above, that's 34%. So your answer here is just 34%, or you could write 34/100ths. And then for the last one, the very last one here, we want the probability, here's our value, probability that our value is greater than the mean plus a standard deviation. So here's my mean plus a standard deviation. So we want really all of these values right here. So we know that this one is 13.5%. The next one is 2.35%. And then this last little tiny piece right here is 1/1500ths of a percent. So we're going to add those three up, 13.5% plus 2.35% plus 1/1500ths of a percent. And if you add those up, you get 16%, or again, you could write it as 1/1600ths. Okay, let's flip over our frame and look at the next side. So on this side, we're just going to interpret normal distributions. So we're still using the same thing. This problem says math scores. The math scores of the 2004 SAT exam are normally distributed with a mean of 518. So notice right here, right in the middle, there's our mean. You will sometimes have to construct these tables, and whenever a word problem gives you the mean, you put it right in the middle. A standard deviation of 114. So here, we did 518 plus 114 to get 632. On the other side, they did 518 minus 114. And then they kept adding 114s to get 746 and 840. Kept subtracting 114 to get 290 and 176. And that's how they completed their curve. So A says, about what percent of the test takers have scores between 518 and 746? So 518 to 746 would be these two slices right here. Okay? We're looking at those two slices, and if we look how much each one's worth, the larger is worth 34%, and the smaller is worth 13.5%. So if you add those up, 47.5% of our test takers would have scores between 518 and 746. For the next problem here, about what percent of the test takers have scores less than 404? So 404 is right here, and we want all of these values less than 404. So if you look at your curve, okay, those three values that we need to add up are 13.5% plus 2.35% plus 1/1500ths%. And if you add those up, you get 16%. Again, you could write that as 1/1600ths. Okay? Now we're going to look at something a little bit different. Okay? Well, for the last examples, we were talking about values that were exactly standard deviations away from the mean. So exactly one standard deviation away or two standard deviations away, above or below. Now we're going to look at what you can do if you have a value that's not exactly one or two or three standard deviations above or below the mean. And to do this, we use the standard normal table, which is listed here. So use standard normal distribution. The standard normal distribution is the normal distribution with a mean of 0 and a standard deviation of 1. So to transform x values from a normal distribution with x bar and a standard deviation of sigma, we're going to use a formula to find the z-score. So this score can be used to find probabilities from the standard normal table. So this you need to memorize. This is how we transform information that has any mean, really, at all, to having a mean of 0 with a standard deviation of 1, because then we can use the standard normal table, and the table is in your textbook. It's not in your notes, but it is in your textbook. Okay? So the standard normal table gives a probability of z being less than or equal to the given value. Draw a picture to help you analyze the values from the table. So we're not going to draw a picture, but I'm going to highlight that last thing that I just said. Okay, the standard normal table gives a probability of z less than or equal to your value. Okay, less than, the probability of it being less than or equal to the value that you want. Okay, so let's look here. So we've got a problem. It says height. A survey of a group of women found that the height of a woman is normally distributed with a mean height of 64.5 inches and a standard deviation of 2.5 inches. So we're going to let x equals a woman's height. So there should be a t here. Let x equals the woman's height. So if I were to fill in my standard normal curve here, this middle, I would have 64.5, because that's my mean. And if I add a standard deviation, I get 67. If I add another one, I get 69.5. If I subtract the standard deviation, I get 62. And if I subtract another one, I get 59.5. So I'm putting these values on here just to show you, for this first problem, we want the probability that our value is less than or equal to 58. Okay, 58 isn't one of these exact values, so we need to find the z-score. So our formula is z equals our value minus the mean divided by our standard deviation. Okay, so our z-score, our value is 58 minus the mean for this problem is 64.5, and divide that by our standard deviation, which is 2.5. So z equals, if you simplify that, you get negative 2.6. Z equals negative 2.6. So here's our z-score. We now need to use our standard normal table to find what the probability of being less than 58 is. So I'm going to highlight here so you can see how I use this. So negative 2, I'm going to look at right here. Here's negative 2. So I'm going to have to use something in this row right here. Behind the decimal, I have 0.6, and 0.6 is right here. So that's something in this row. So if you notice, those 2 points intersect right here. Okay? So the probability that z, that our value is less than or equal to negative 2.6 is this. Okay? And because we transformed from 58 to negative 2.6, this is the probability that our value is less than or equal to 58 inches. If you wanted to change that to a decimal, it'd be 0.47%. It's not very likely at all. Let's do the next one here. Okay, so we want the probability that our value is between 65 and 72. Okay, probability that our value is between 65 and 72. So we've got to find z-scores for both 65 and 72. So let's find our z-score for 65. We're going to do 65 minus our mean divided by our standard deviation. If you do that, that's 0.2. Okay. Now, we're going to find the z-score for 72. So that's 72 minus our mean divided by our standard deviation. And that's 3. Okay? So we're going to do the probability of 3 minus the probability of 2/10. So the probability of 3, we're going to have to look at our table. So find 3 down the left column, okay? And it's 3.0, so it's this value right here, 0.9987. Okay, that's the probability really of it being less than 3. Okay? So the probability of it being less than 3, which is the probability of being less than 72, it's the same thing, they're equivalent, is 0.9987. But we want to subtract the probability of it being less than 65, which we used our z-score and we converted that. That's the same as the probability of 2/100ths. So, or I'm sorry, 2/10ths. So 2/10ths is right here. So it's 0.2. And looking here, it's going to be one of these values, but the number before our decimal is 0. And since it's positive 0.2, it's right here, because that would be 0.2, positive 0.2. So minus 0.5793. And if you subtract those, you get this. So that's our probability of our value being greater than 65 and less than 72. Okay, well, let's look at the next one here. We want the probability of our value being greater than 63 but less than 74. So we can find the probability of it being less than 74, but then we have to subtract from that the probability of it being less than 63, because that's the values that we don't want. So let's find the z-scores for both of them. So my z-score for 63 is 63 minus my mean divided by my standard deviation, and that's negative 0.6. So my z-score of 74 is 74 minus my mean divided by my standard deviation, and that's 3.8. Okay, so we're going to do the probability of 3.8 minus the probability of negative 6/10. Okay, that will give us the probability really of 74, taking away the probability of it being less than 63. So if you use your table, 3.8, find 3 along the left column, okay, and then go all the way over to 0.8, and that's 0.9999. And we're going to subtract from that, okay? We've got negative 0. So negative 0 is in pink, and go all the way over to where it says 0.6, and that's 0.2743. So if you subtract those, you get this. So this is our probability of our value being greater than 63 but less than 74. And that's really 72.56% if you would like to see things as a percent. Just like the last one was really 41.94%. Let's do our last one here. So for this last problem, we want the probability that our value is greater than or equal to 72. Now, remember I said earlier, our standard normal table gives us our probability that our value is less than 72. So what we really want here is we want 1 minus the probability that x is less than or equal to 72. So we're going to do 1 minus whatever the probability is. Okay? So let's find our z-score for 72. So 72 minus 64.5 divided by sigma. If you simplify that, you get 3 exactly. Okay? So the probability for 3, if we use our table, that's really 3.0. So for 3.0, it's 0.9987. And like I said, that's the probability of our value being less than 72. The probability of our value being less than 72 is not what we want, though. So we're going to do 1 minus this value in order to find our probability of it being greater than 72. So that's 0.0013, which is 0.13%. So that is not very likely. And this is the end of lesson 11.3. Please make sure if you had any questions at all, you start it so that we can talk about them tomorrow in class. Getting used to using this table might take a little bit of time. Have a good night.